So any questions before I get going? So I sent an email out about this. There's going to be a star party on Thursday night, so we'll have a few telescopes out in Aldrich's Park. This is an event that's sponsored by ASUCI, but also the UCI Observatory folks are going to be out there. And I'll be out there for a few minutes introducing the targets that we're going to be looking at. So we'll have a telescope pointed at Jupiter. And you can see Jupiter through a big telescope. If you've never done that, it's really cool to see. You'll be able to see the Galilean moons of Jupiter. And I'll talk a bit about how cool a couple of these things are. Another one of the telescopes is just going to be pointed at the moon. But if you've never seen the moon through a telescope, that's definitely worth doing. I mean, it's pretty cool. You can see a lot of detail. And finally, we're also going to be pointed at a star. And this is a star that's known to have a few big planets orbiting it. And so you won't be able to see those planets with the small, teeny telescopes that we have. But at least you'll get a better sense of the color of the star, and I'll be able to say a few things about what we know about those planets. If you come to this event, we'll have a sign-up sheet, and if you're there and you write your name down, you'll get a little bit of extra credit for this course. It's not going to be a lot of extra credit, but it'll be a little bit, just a little bit of extra incentive for you to come. So it'll be Thursday night at 8:30 outside in the park, basically just right out here. If you come down these stairs right here to the park, you'll see some telescopes. It'll be easy to find. It'll probably be going on until about 9:30. So you can, if you want to, you can show up anytime in that hour and take a look at stuff. You've also got a homework assignment that's due Thursday. I think it's due at 5 p.m. So before the like star party. So you won't be like missing out on doing your homework if you come look through the telescopes for a few minutes. Okay. All right. Any questions about that? Okay. So this is lecture 5, and the title of lecture 5 is The Sky Above and the Earth Below. And we're going to transition now in this course from talking mostly about sort of historical trends and our sort of the development of the modern sciences. And now I'm going to be talking a bit more just about the things that we learn and what we know about the Earth that we're inhabiting, and things we've learned over the last many years of studying the Earth, etc. But of course, keep in mind that all of these things that we know, we don't, that the reason why we know them is they come about from a process of experimentation and study in a very detailed and careful exploration of the world around us. And at times, I will sort of pause and talk a bit about how we know some of these things. But if you have questions about this stuff, please do ask. So this is sort of a big picture of what we're going to be talking about today. And if you look at the Earth, right, it's mostly a solid object. And there's just this teeny tiny little layer on the top of the Earth that is our atmosphere. Most of the Earth is sort of solid or semi-liquid. So starting at the very top, we have the atmosphere, and then we have the oceans and the land. Something like 75% of the surface of the Earth is covered with water. You all know that. And then we get a little bit of land on top of that. But most of the Earth is actually not water, right? So even though from above it looks like it's a lot of water, by mass it's really not mostly water at all. So just below the rocky crust here, there's something called the mantle. And then below the mantle, there's a liquid metal core. And then finally, there's sort of a solid metal core at the very middle of the Earth. And so in the first part of this lecture, which will be sort of the bulk of the lecture, I'm going to be talking about, as you sort of drill down, if you can imagine drilling down into the Earth, what would you see? And why does this matter? Okay. So one thing to keep in mind is that the Earth is pretty strongly differentiated. And so parts of it are solid and parts of it are liquid. And this matters because the interior of the Earth is a pretty dynamic place. And because we have this kind of dynamic Earth, that actually matters a lot, we think, for the existence of life on Earth. And I'll talk about why that is. One of the main reasons why having a dynamic Earth or a dynamic interior of the Earth matters for us is it creates a magnetic field. So the Earth has a magnetic field, it permeates it. The Earth's magnetic field is why you can have a compass, and the compass basically tells you which way is north. Okay? But this magnetic field does something more for us than point compasses. The magnetic field protects the Earth from charged particles. So there are charged particles that are streaming from the sun and hitting the Earth, but they get captured by the magnetic field and redirected. And if it wasn't for this, then our atmosphere would be getting blasted off constantly by something called, these charged particles that are called the solar wind. If you look at other planets in the solar system that aren't so lucky, they look very different than us. So for example, Mars is a planet that doesn't have much of a magnetic field, effectively no magnetic field, and it also has effectively no atmosphere. And having no atmosphere is not so good for life. Another thing that's important on the Earth is that it has a crust, but this crust, yeah?
So when you say it gets blasted off, do you mean that like the air is literally getting shot into space?
Yeah, so you have these charged particles that would be streaming in, and there are molecules in the air, and there would be a collision there, and it would provide energy to those particles and basically launch them off into space. They would no longer be gravitationally bound to the Earth. Yeah, that's what I mean. Yeah, so it's good that we have a magnetic field because it protects us from that onslaught, you know. So then I was talking about the Earth's crust. So if you think of the Earth's crust, you can think of it like the shell of an egg, okay, and imagine it's cracked. And unlike an egg, you can imagine what if the inside of that egg was sort of churning and was sort of semi-liquid and had some kind of convection going on. Then the crust of the shell of the egg would be pushed around and moved around. So the tectonic plates on Earth are being pushed around and moved around. And this matters for the overall geography of the Earth and, in fact, affects what's even in the atmosphere of the Earth. The boundaries of these plates are basically where we have a lot of earthquakes and volcanoes. And so you probably know that we live basically at the boundary of one of those plates. Okay, we're near the San Andreas Fault. And we're sliding along. We're actually on the Pacific plate, and we're sliding along the North American plate, and that's why we have so many earthquakes around here. Now, starting from above and looking down on the Earth, one thing is pretty obvious: that the Earth is mostly water, in the sense that the surface of the Earth is mostly water. About 71% of the Earth is covered in water, and only 29% of the Earth is covered in dry land. Now, I'll just mention this now, but I'll return to it a little bit later. Imagine a scenario where the Earth formed, okay, and somehow we get water on Earth. And it turns out water exists all over the place in space. One possibility is that we actually got our water from comets that are filled with ice that slammed onto an early Earth that delivered water onto the Earth. But you see water around young stars, et cetera, throughout space. So water exists. It's a pretty common thing in the universe. And we have a fair amount of it. But you can imagine a situation where we had just a little bit more water. Okay? Imagine we had twice as much water on Earth. Okay? Imagine you created a new Earth, and for some reason the ingredients were a little bit different. We end up having twice as much water as we have today. We'd have a very different world, right? Because then there would be no dry land. So we would have what astrobiologists call a water world. Now, if you had a water world, the life that would evolve on this world would be very different than at least the life we have on land today, right? I mean, you would not have sort of things like us walking around on land because there would be no dry land. Everything would be underwater. And if you take a look at the creatures on Earth that have evolved to live underwater, they're different than the creatures that live on land. And even though dolphins are very smart, they haven't built any radio telescopes or rocket ships, as far as we know, right? So this issue of how much water we have and the fact that we're not a water world is interesting. Also, you could imagine that if we lived on a planet that was a lot like ours, but just was endowed with, say, 10 times less water, then the prevalence of life would also be a lot different, right? There would be a lot less water on Earth, many fewer places for life to have gotten a foothold because of that water. And you would imagine that that world would be a lot different than our own as well. So when you take a look at what we have in comparison to what we could have had, it's just sort of something that we have to keep in mind in these kind of, you know, in a class like ours where we're thinking about life beyond Earth. Why is this not clicking? Okay. Now, here's something you may not have realized. It's true that most of the surface of the Earth is water, but if you took all of the water on Earth and rolled it up into a ball, okay, this is what it would look like in comparison to the Earth itself. So we think of the Earth as being endowed with all this water, but really it's not much water at all. And moreover, if you look at all the fresh water on Earth, it's just this much. So you're probably aware that we're undergoing a pretty serious drought right now, and so our concerns about how much fresh water we have are pretty big ones. And it's, you know, it's realizations like this that make you a little bit nervous, right? One of the problems, of course, with when you have a drought is when it rains, a lot of the rainwater just rushes to the ocean, right? So if you don't catch that water and do something interesting with it and you allow it to just flow down drains and go into the ocean, which, by the way, is an important thing to happen, that water runs out to the ocean, it mixes with the salt water, and now it's salty and you can't drink it anymore. And it's much, much harder than then turn that into potable water once it mixes into the ocean. So what we've got to deal with in terms of water on Earth that's fresh is just a teeny amount compared to the salt water. Now if you dig a little deeper and you look at the content of the Earth itself, well, this is what the Earth is made of by mass, okay, in terms of its elements. Most of the Earth by mass is actually oxygen. And the next big chunk of the Earth, almost equal to the, sorry, did I say oxygen? I meant iron, that heavy stuff, iron. So most of the Earth by mass is iron. But almost equal to that is oxygen, okay? So a bunch of the mass of the Earth is in oxygen, about a third of that. And the next big chunk is silicon, okay? And then these other elements somewhat less than that. So the big ones are iron, oxygen, and silicon. I'll just note right now, and I'll return to it later, we've got a lot of silicon on Earth. As I'll discuss in a couple lectures, people talk about the idea of a different kind of life that's not carbon-based life, but silicon-based life. Because silicon behaves a lot like carbon does chemically. And so if you read a lot of science fiction, occasionally you'll read about, as opposed to silicon-based life forms as opposed to carbon-based life forms. This is an idea that's percolated. It's interesting, though, that we have so much silicon, and yet the life on our planet is basically carbon-based and not silicon-based. So that tells you something, that there's something special about carbon, even more than silicon, that seems to be amenable to life, at least on Earth. The Earth's surface is mostly made of silicates, iron-rich basalts, and carbonaceous rock. I'm not going to get into the types of rocks that make up the Earth. There's whole, you know, classes you can take on geology and the different types of rocks that exist on Earth, etc. I'm just sort of going to glance over that stuff here. But just so you know, there are these different types of rocks that are known to exist on the Earth, and the formation processes of these rocks have to do with sort of the cycles that exist on the Earth. And I'll return to this just a little bit more later in the course, but just to sort of give you an overview, there are these different kinds of rocks, and most of the Earth's surface is sort of either silicate rocks, iron-based rocks, or so-called carbonaceous rocks. So this example, for example, is limestone. If you look inside the Earth, it's a pretty active and interesting place. So it's hot, so it's hotter in the middle of the Earth. It's denser because it's got all that pressure going on. And it's stronger differentiated. That means there are places where there are light silicates, so the silicate kind of rocks are lighter. Okay? And then there are heavy metals that are somewhat heavier. And so this creates a tendency you can have things that are buoyant or not, floating or not within these structures. Okay? I'll return to these names again, but there's basically, we believe, a solid iron inner core, a liquid iron outer core, and then this big structure that's called the mantle, and then just on the top of that is the crust of the Earth that we're most familiar with. Now, here, this sort of drills down and gives you sort of depths here. So the crust, the thing that we live on, is about 100 kilometers deep. So that's the crust, that's the surface of the Earth, that's where we live. Okay, it's 100 kilometers deep, so you know it's pretty deep. And that's mostly made of silicate rocks. Below that is the mantle. And that's sort of this kind of mushy stuff that I'll return to a bit. But it's not really a liquid, but it's mushy and sort of malleable. And it contains actually a bunch of the mass of the Earth. About 67% of the mass of the Earth is made out of this mushy silicate stuff that we call the mantle. And that goes all the way down to about 2,900 kilometers. Then we have the outer core of the Earth. That's molten iron. About 30% of the mass of the Earth is there, and that gets you down to 5,100 kilometers. And then finally the inner core, which is solid iron. It's only 2% of the mass of the Earth, and then we get down to the 6,370 kilometers, which is basically the radius of the Earth. Okay, so this is just the depth. Now, something to keep in mind is the deepest. You might wonder, have we ever dug down in there? Like, how do we know this? Do we just dig a giant hole and, you know, stick a thermometer in there? Like, what do we know what's going on? Well, that's not really how it works. The deepest hole ever dug is about 12 kilometers deep. The crust is about 100 kilometers in most places. So we have not yet reached the mantle with a hole. So if you talk about, you know, people talk about digging a hole through the center of the Earth, that's not going to happen anytime soon. There are all kinds of ongoing attempts for people trying to dig these deep holes. If you Google this, like there's like, you know, pages and pages of stuff that cover, you know, people geek out on like digging deep holes. They're trying to reach the mantle because it's interesting. You know, geologists are interested in knowing, like really sampling the mantle. And they're actually trying to do this in the middle of the oceans. So the oceans tend to have the thinnest crusts. And so it turns out that that's a good place to try to dig really deep holes. You try to go in the middle of the ocean and dig your deep hole there. But obviously that's not so easy to do because you're in the middle of the ocean. So you might wonder then, well, if we've never dug in there, how do we know this stuff? How do we know what the middle of the Earth is made of? And so I'll talk a little bit about how we know some of those things now. It turns out that we can use seismic waves. So in much the same way that, you know, doctors use sonograms to learn something about, you know, what a baby looks like and how your baby's doing in there, you can use sound waves by bouncing and reflecting sound waves off the Earth through the middle of the Earth to learn something about what's going on in there. However, we can't just take a giant, you know, sound wave machine like we have and run it over the outside of the Earth like you do when you're looking at a baby, right? You can't do that. Instead, the Earth actually provides us with sonic waves of its own via earthquakes. So when there's an earthquake, and I haven't yet talked about where those earthquakes come from, but basically you have these plates that I talked about before, and sometimes they shift and move. And when you get one of these shifts, it creates sort of a propagation, a disturbance of propagation through the Earth. And there's basically two types of sort of distorting waves that propagate through the Earth when this happens. And they're called S waves and P waves for short. Now an S wave is associated with something called shear. So an S wave is a shear wave. And shear waves are like, you know, imagine you've got a block of rock or something that's semi-solid and you sort of shift it down and up. So this would create an up and down shearing sensation. So it's sort of side-by-side shearing. Okay? And so, well, what happened? Is that what you were telling me about? Thanks. I don't know why that happened. Thank you. Right, so then that's what this picture is here. So, and when this happens, the interesting thing about this that I'll return to again is that kind of thing can propagate through both liquids and, it can propagate through solids, but not through liquids. Okay, because you imagine like if you've got a pool of water and you tried to grab some of the water and shift it to side, well, your hands would just go like this and it wouldn't really propagate. You know, you wouldn't get some disturbance propagating like that through the water. Whereas if you're holding on to some, you know, if you were strong enough to sort of shake rock, that would propagate through the rock, right? However, there's another kind of wave that's called a P wave, which is a different kind of pressure force. So imagine now, you know, you could imagine if you wanted to, if I wanted to shake this table, there's two kinds of things that you would generally do. Any way I shake this table, it's either going to be a side-to-side motion or a forward motion or some combination of that, right? Any way I shake this table, you could break it up into some motion that's like that and some motion that's like this. So the second kind of motion, rather than the side-to-side shearing motion, would be sort of a pressure wave motion, so a push. So that kind of wave will propagate through solid rock too, but it will also propagate through water. So if you're standing in a swimming pool and you give it sort of a push like that, you can imagine that sort of pressure wave propagating through the water just as well. So the point is, whenever there's an earthquake, there's two types of waves, that would propagate through the Earth. One would be a shearing kind of wave that would be sort of side to side or up to down, and the other one would be a pressure wave that would be sort of back and forth. These pressure waves pass through both solid and liquid, whereas the shear waves only pass through rock, and in fact when they get to a liquid boundary, they would bounce back. So what this means is that if you have an earthquake, which generates both S waves and P waves, and then you have stations all over the Earth that are sort of detecting these disturbances, you can begin to get a picture of the kind of material that those waves have to pass through, right? So we believe that there's solid here, liquid here, and then mantle, which is also basically liquid. So if you have an earthquake here, then a station at this point would detect both S waves and P waves. It would be both pushed and sheared. Whereas if you had a station over here, you would only detect the P waves because the S waves would not make it through. And similarly, a station here, you would again get S waves and P waves. So you could imagine that if you had a surface of the Earth that was covered with these detectors, things that are looking for this seismic activity, you could then begin to map out, well, what part of the Earth is liquid, what part's solid, and begin to get a deeper picture about the makeup of the Earth. Another thing that's important, and I won't go into too much detail, is that the speed with which these waves travel are also sensitive to the makeup of the inner part of the Earth. And so you can get timing, you can get types of waves, and by getting a really detailed picture of all this stuff, you begin to map out what the Earth is made of, basically with a sonogram. Yeah?
Is that how we know also how the center is solid?
Yeah, because we know that it's solid because you basically never get S waves when you're directly across the Earth from a place that has an earthquake.
That solves the liquid question, not the solid question.
Oh, I'm sorry. Yeah. So, so we're actually thank you. So we're actually less 100% sure on the very inner part of the Earth. So that's sort of a debated thing. And so that actually comes from modeling. So that comes from sort of detailed modeling of what we think the inner part of the Earth would be given the pressure that it's under, and et cetera. So we think this inner sort of solid part of the Earth issue is more debated and has to do with this sort of I'm trying to think of the right term. I don't know why I'm blanking on this. What the hell's wrong? Anyway, so you can do mathematical models of what you think the structure of the Earth would be under a given pressure and constituents. So you know what the gravity in the Earth is, you know how much heat is there, et cetera. And so given the pressure that this piece of material is experiencing, how much weight it's bearing, and what we think it's made of, given its temperature, et cetera, you can sort of calculate whether or not you think those constituents should be liquid or solid. And the best estimates right now is that probably at the very core it has to be solid. So if you know the temperature of something and the pressure it's under, you can calculate whether it should be solid or liquid. And that's where this issue comes from. Yeah, thanks. Sorry about that. Other questions? Okay. Here's just an example of how you might go on about do this. Imagine this is actually a series of detections that were made when an earthquake went off here. So here you've got an earthquake that happened in Sri Lanka, okay? And so all the seismographs are going off in Sri Lanka. And what's plotted here is time. So it's minutes since the original earthquake went off. And then this is another detector that's some distance from Sri Lanka. Okay, and so over time you see this propagation kind of bounce around, and what you'll see is it actually bounces and goes all the way around the Earth and comes back to Sri Lanka again, and that's what you see here. So you see this wave actually propagate through the Earth and back again. So it's going forward and backward and forward and backward, and then you can sort of see it bounce around. And then of course you see it die out over time. So the shakes right when the earthquake happened are much bigger, and then you see it begin to die out over time. Now, the fact that there is this molten region right around the core of the Earth is very important. When you have something that's that hot, okay, that means it can move and flow. So the Earth is turning, right? So you've got that kind of structure. And then also, I haven't talked much about it, but when you have something that has a temperature profile, you also tend to get something called convection, which I'll return to before, but you just get sort of a mixed up situation within the Earth. So we have an Earth that's turning, and therefore we've got this liquid material that's also sort of spinning around. Now, when you've got a hot sort of metal that's effectively so hot that it's going to have some charged particles moving around, some free charged particles, this creates a magnetic field by a process called a magnetic dynamo. Okay, so it's got a molten core that's conductive, okay, and spinning, it's churning, and so you have these charged particles that are spinning around. Whenever you have charged particles that are spinning, that creates a magnetic field. Okay, you can create magnets this way. So if you've ever seen this experiment, if you take a loop of wire and run a current through it like this, it will create a magnetic field, and if you put a compass next to it, you'll see that compass needle align to that. Okay, so this is a well-known property of currents and electromagnetic fields. So the point is, because we have this liquid core, it's hot enough in the core of the Earth to have liquid molten stuff. There's charged particles in there that are now spinning around. We have charged particles spinning around, moving around inside the inner Earth. That generates a magnetic field. And so the coherent motion of these charged particles in the Earth generate a magnetic field that has a structure that kind of loops around like this. And this is sort of a diagram of how the magnetic field of the Earth looks from outer space. So generally there's a north pole of the magnet that's roughly pointed towards the North Pole, and then there's a south pole of the magnet that's down at the South Pole, and that creates this sort of magnetic structure on the Earth. The north magnetic pole is a little bit different than the geographic North Pole, so they're not perfectly aligned, and you probably are aware of this, right? So magnetic north is different than absolute north by a few degrees. Yeah?
Is the geographic North Pole the axis that it's turned on?
Yes. So it's the pole of the Earth, like you have an equator, right, and we're spinning around it. So it's that pole, the thing we're spinning around. Now, as I mentioned before, this magnetic field is really important because it protects the Earth from these charged particles that are streaming from the sun. So here's the sun, and the sun is blowing off this solar wind. There's all these very high energy charged particles that are coming at the Earth that it's blowing off in actually all directions. They're hitting all the planets. But the nice thing is that we have this magnetic field, and the magnetic field is basically guarding the Earth from a lot of these charged particles. Now, a lot of times, actually, when a charged particle encounters a magnetic field, they'll begin to circle around those field lines, and they kind of loop around them and track the field lines. So rather than going through them, they'll tend to track them, loop around them, and follow them in a loop around. And when that happens, those charged particles tend to get directed in the direction that the magnetic field is going. So they'll be coming in this way, and then they tend to get channeled along to the poles of the Earth. So they'll come in, and some of them will get channeled this way, and they'll come into the atmosphere up here, or they'll get channeled this way, and they'll come into the atmosphere down there. And you create, and in the North Pole and the South Pole, especially if this happens, if it's a winter time, if it's dark, then you'll see these beautiful auroras. Has anyone ever seen an aurora, like Aurora Borealis, been far enough north where you could see these in a dark enough place? You have? Cool. Where were you?
Alaska.
Cool. So you were in Alaska in the winter?
Yeah.
Cool. Was it dark the whole time you were there? You were far enough north where it was it
It
like,
wasn't too far north.
okay, but you could still see them. That's cool. Yeah, that's lucky. That's cool. Yeah, so these auroras are beautiful, but you tend to only be able to see them if you're far enough north to be in a place where they're being channeled down by these fields. Occasionally, there'll be a giant solar storm where so many charged particles will come that you will actually be able to see an aurora at pretty far southern latitudes. You can see them even like in southern Canada and even in the northern United States. And occasionally, there's on record where people could see auroras all the way down in Florida for really giant solar storms. So it's crazy. But most of the time, you will not see an aurora unless you're really far north. And it usually has to be the winter time because it has to be dark to see it. So you'll see these both in the north and the south. And cultures that live either in the far north or it's less often, but in the far south where you see these things, they all have names for these auroras, and sort of intimately entwined with their cultures because it's sort of a glorious and amazing thing to see. This is an image of the Earth taken from space, now of the southern hemisphere. So this is Antarctica, and you see this ring of interact. So what's happening here is the charged particles are coming and hitting the atmosphere and basically ionizing atoms, like knocking electrons off the atoms, and that's producing light, and that's glowing green in this particular case. And the crazy thing about these auroras, I guess when you saw them, was it moving a little bit? Like, yeah, so it does. It sort of looks alive in the sky. Okay. So if you've got, so I have little kids, little girls who love the movie Frozen, and in the movie Frozen, the movie opens up with an aurora borealis, and the aurora borealis is making the sky green. Okay. So I was so wanted to pause the movie and give a whole lecture on the aurora borealis, but I didn't. I could scar my kids for life with that kind of activity. So, but the point is that it's not a very stable situation, right? And so there are the field lines kind of get shifted around and they get shaken around because they're interacting with these fields. And so it's not a stable thing. It looks alive, like it looks sort of fluctuating and moving because it's such a dynamic process. So you can imagine a situation where the Earth's magnetic field didn't exist. Okay, so imagine you waited a really, really long time and the center of the Earth cools off so much that we no longer have a liquid core. So we no longer have any liquid molten material in the core, and so that magnetic dynamo basically shuts down. Then we'll have less of a shield for the solar wind, and you would have that solar wind then interacting with all of the atmosphere all the time, and eventually you could imagine that really disrupting our atmosphere. And our atmosphere does a lot of good things for us. It shields us from ultraviolet radiation and other kinds of radiation, but also it provides a very important pressure to allow us to have liquid water, which I'll return to again later. But the point is, having this magnetic field, having this molten inner Earth is very important, we think, for the existence of life on Earth, especially the existence of life on land. The water itself shields stuff underneath the water. So even without a protective atmosphere to keep the UV out, if you have liquid water on your planet and you live beneath that water, the water itself will shield you from UV radiation. Okay. So the very upper crust and upper mantle of the Earth is called the lithosphere. I'm not going to test you over that name. I'm just for completeness. You don't have to know lithosphere or asthenosphere either. But just for the sake of completeness, this lithosphere is the crust and upper mantle of the Earth. And just below the lithosphere is the asthenosphere. Okay, so it's sort of this layer right here. Now this layer is kind of interesting. So it sort of acts like silly putty. It's sort of a very interesting constituents when if you take it and you move it very slowly, right? If you take silly putty and you stretch it very slowly, it almost behaves like a liquid. You can stretch it out and it sort of behaves like a thick flowing liquid. But if you were to take a hammer and smack silly putty, it will crack. So it has this kind of, so if there's a sudden shock, it'll crack, but under smooth situations, it'll just sort of stretch and pull. Now, the other thing that's going on in this region is there's something called convection. If you've never heard of convection before, it's a very important idea, and it's sort of, you'll see it happen again and again. It happens in weather, it happens on the Earth, and it's a pretty simple idea. So imagine you've got a pot of water, all right, and you've got a heat source underneath it. The water that's at the bottom of the pot feels this heat, okay, and that water, once it gets hot, gets a little less dense, and therefore it rises up. So it rises up to the top, but now it's up to the top, where the heat source is down here, so it's being heated less, and it begins to cool off. It's near the top of the water. Now as it cools off, okay, it gets dense again and falls back down. And so you have this process where when it comes back down, it gets heated again, then it goes back up, and it creates a system that sort of churns. So that process is called convection. So a pot of boiling water is not a stable thing, right? It's not like the hot water is at the bottom and the cold water is at the top. That water is mixing itself up all the time because of this convection. Now the same thing's happening, okay, in the asthenosphere, because the inner part of the Earth is hot, and it's also cooling off at the top. And so you have stuff getting hot at the bottom, getting heated up and churning up here, and then cooling off and coming back down. And that creates this convection within the Earth as well. So there's some turbulent something going on beneath the Earth's crust. Now, the thing that's driving this convection, okay, that's an energy source, right? So it takes energy to make this convection happen. What's driving this? What's creating the heat? It's actually radioactive decay of uranium, mostly. And there's also thorium and potassium decay. So these radioactive decays, remember we talked about radioactivity before, there's uranium that's decaying and that's producing energy. And it's specifically uranium-238 decaying is generating most of the energy that drives convection on the Earth. So what's happening here? So we have an energy source from this radioactive decay, and that's heating stuff up, making it rise, then it cools off, then it falls back down. And this is a pretty complicated system, you can imagine. But there are places that are called ridges, which are sort of dividing lines where stuff's coming up, and then it sort of parts ways there. Okay, and that creates something called a ridge. And then on either side of that ridge, the plates that are sitting on top get pulled away from it, so they move away. And then you can imagine another place where plates are colliding. And when plates are colliding, that's another place where interesting stuff happens. Now, convection underneath the crust of the Earth has broken up the crust into a bunch of pieces. And this was this eggshell thing that I was talking about before. There are 16 plates, so-called tectonic plates, that break up the surface of the Earth. So the lithosphere has 16 plates that it's broken into. And because these plates are sitting on top of this thing that's convectively bubbling along, they're shifting. They're shifting along. So now in your pot of boiling water, right, you've got some stuff floating on top of it that's shifting around as the water's boiling. These are the things we live on. So here are all the plates, okay? Lots of different names. There's 16 of them. I'm not going to test you over the names of the plates. Something you might want to know is that we are here. So we live on this Pacific plate here that's running up against the North American plate. Now, these plates are floating on top of the mantle, and there's basically two kinds of plates. There's oceanic plates, so the ones that are under the water, and then there's the continental plates, okay? The oceanic plates tend to be younger and thinner. Remember how I mentioned that when we're trying to dig really deep holes, we usually do that in the ocean? That's because the plates in the ocean tend to be younger and thinner, and they're only 5 to 10 kilometers deep. The continental plates are like 20 to 70 kilometers deep, so they're a bit thicker. And so they're moving around. It's a pretty complicated situation. Now, they're all moving relative to each other. So these are actually rough estimates of speeds that have been obtained by studying particular markers, and you see them move with respect to other plates over the course of a year. And they're moving at a speed of something like 4 centimeters a year. That's a typical speed of one of these plates. Okay? So you see, for example, that the plate we're on is kind of moving this way, and the plate we're running into is sort of moving this way. Now, how fast are they moving again? 4 centimeters a year, that's like 1.5 inches a year. So they're not moving very fast, right? So that's why it doesn't feel like they're moving. It feels like the ground is steady. But of course, the Earth has been around for a long time. Okay? So they've moved pretty far, and I'll return to that in a bit. Now here's the Earth tectonic plates, all right? Interestingly enough, if you plot where earthquakes are measured, that's where the earthquakes happen. Okay, so the earthquakes on Earth tend to happen along plate boundaries. Not every single time. Every now and then you get an earthquake like in Ohio or something. That's sort of weird. But most of the time when you get earthquakes, they're right along these plate boundaries. Yeah?
Why are earthquakes more prominent around certain plate boundaries
Than others? They tend to be, like for example here, this is where the Himalayas are being built. So that plate is just coming right at the other one. So sometimes the interactions are just more drastic, So it just depends on the interaction between the plates. Sometimes they're coming at each other, sometimes they're sliding along, and you get different types of earthquakes and different types of activities depending on the relative motion of those plates. But yeah, I mean, there's clearly, this is really an active region here. Amazingly active. This is where volcanoes are located. Okay, so volcanoes often tend to be located also along these boundaries. But again, not always. There's different kinds of volcanoes, but a lot of times you'll get volcanoes where these things happen too. That's cool. Now, I talked about the speed of these things. You're like, oh yeah, an inch a year, that's not very far, and that's true. But the Earth is old, right? And so it has a long time to get where it's going. So if you've got something that's moving at 4 centimeters a year, remember distance is rate times time, and we've got a long time. So imagine, let's just do an example. Imagine you've got a plate that's moving at 4 centimeters a year, and you want to ask how far has this plate moved in 500 million years? 500 million years is 5 times 10 to the 8 years. Okay? So the distance the thing has traveled is the rate, 4 centimeters a year, times the time, which is 5 times 10 to the 8 years. Okay? If you multiply these together, okay, it's 10 to the 8 times 4 times 5, so it's 20 times 10 to the 8, or 2 times 10 to the 9 centimeters. That's 2 times 10 to the 4 kilometers. That's a big number. That's half the circumference of the Earth. So in the last 500 million years, a single plate could have moved halfway around the Earth. And they're all moving. So you could say to yourself, wow, things were probably different 500 million years ago than they are now in terms of where the plates were, where the continents were. And in fact, there are people who are modeling this to try to estimate what things were like well in the past. And the best guess right now, that about 300 million years ago, all of the continents were together in a single gigantic continent that's called Pangea. And that's why, if you've ever, I remember being a kid and looking at the continents and always imagining, boy, look how South America just would fit right in Africa. I remember just sort of, maybe just putting puzzles together all the time. You can see that they almost look like they would fit together. And it looks like all of them were kind of crunched together into a single continent about 300 million years ago. This is just an example movie of running things back in time, the last 600 million years, of how we believe that these continents were all put together at one time in the past. And that's how we get to where we are today. Notice how the glaciers are changing over the course of time. So we have these periods of great glaciation popping up, and those are going away. So it's all part of this very complex historical cycle that we've had here on Earth that affects the climate and other things. You start moving the continents around, you start changing things as well. Now, as we mentioned before, interesting stuff tends to happen where these plates are coming together. They're sliding by each other, they're ramming into each other, and when this happens, interesting things happen. So exactly what happens depends on how the two plates are moving relative to each other. Are they moving away from each other? Are they moving towards each other? Are they moving side by side? So for example, when you have plates that are moving away from each other, you create these things that are called rift valleys. And so there are famous places that are rift valleys that exist that you will see periodically, on the globe, okay, where rifts are coming apart and create these kind of giant valleys. When plates are moving sideways, that tends to cause earthquakes. Okay, so what happens is you get tension building up over periods of time, and eventually that tension slips and you get a break. Okay, so if you've ever taken two bricks, I mean, I'm sure maybe you've never done this, but imagine taking two bricks and you put them side by side each other and sort of push on one brick for a while. They mostly stick together, and then eventually it'll give and go, and break. So it's those drastic shifts are releasing this built-up tension, and then the ground shakes when that happens, right? And so that's why you want to have a lot of little earthquakes and not one big earthquake. Eventually, this tension is going to be released, and you'd rather it be released a little bit at a time than one big one. So every time there's a little earthquake around here, I'm always pretty happy. I like that. I'm like, okay, good, a little one. Don't want to wait for that big one. Now, growing up I grew up in Ohio in the middle of the country, and it was sort of common knowledge that at some point California is going to fall in the ocean, right? I mean, that's just, everybody knew that. In addition to all that stuff going on with crazy people in Hollywood and everything, and the hippies and whatever's going on in California, it's going to fall in the ocean. So it's just a wild, crazy place out there west. But of course, that's not going to happen. Okay, California's not going to fall into the ocean because it's not moving that way at all. We're moving this way. Okay, so what's actually happening is Irvine is basically moving this way. We're going to move up here in the direction of, say, San Francisco over time. We're not going out in the ocean. We're just moving along this way. So good to know. So we're not going to fall in the ocean. Feeling good about that. I don't even know if that's common lore anymore either. But when I was a kid, it was like common knowledge. Oh yeah, it's going to fall in the ocean. So weird. Anyway, so when plates move towards each other, something different happens. Okay. So when plates are moving towards each other, then you can have the lighter crust tends to slip under the heavier crust. And then you get things pushed up underneath, and that tends to be where you get big mountain ranges, okay? So this is subduction as it comes under. A very sort of a clear example of this is the Himalayas, okay? The Indian plate is slamming up against the Asian plate, and that's creating the giant Himalayan mountain range. The other thing that can happen in areas where plates subduct, okay, up and down motion, okay, is tsunamis. And so where we live, where we have a side-to-side, where we have the San Andreas fault, we're not very prone to tsunamis. So if a tsunami were to hit here, it would be coming from somewhere else across the ocean. Okay, but we're not going to generate a tsunami here offside the coast of Newport Beach. Where you get tsunamis is in areas where the plates are coming together and you get sudden drops. Okay, so suddenly the seafloor drops, then the water shifts down and bounces back up, and that's what creates these big tsunamis. That's the kind of fault that exists up in Seattle. That's the kind of faults that exist near Japan, and so that tends to be where you get the tsunamis in those kind of plates, not the kind of plate that we live on. Now, you may remember this one. This was just an awful one that happened in Japan in the year 2011 that created this crazy earthquake that also flooded a nuclear power plant that that sort of messed up that nuclear power plant and made people very uncomfortable about nuclear power plants for a while because they were concerned with contamination. So this is the kind of, these are crazy tsunamis, just awful tsunamis that you get periodically. Another one that was really just awful was this one in Sri Lanka in 2004. I'm not sure if you folks remember that one. Does anyone remember that one? Yeah, that was really bad. A lot of people died. And one of the things that happens with these tsunamis a lot of times, especially the big ones, is you'll have one of these faults, okay, and the water reacts to that. And so you had a fault that was somewhere way out here, and the water and the surface of the ocean went down, and water rushed towards it. And it takes a while for that water to rush towards it, and then it comes back. And so what happened here was that the tide went way out, and there were all these people on the beach who didn't know what was going on. And people were like, wow, look how far the tide went out, and they went out in it. And it was just awful. And so then the tidal wave came, and these people were just, they were just lost in it. It was really, really horrible. And unfortunately, there were people up here on the mountain, up high, who could see it happening and were sort of on cell phones and knew what was going on, but there was no way to communicate that to the people who had rushed out. So if you're ever someplace that's in a tsunami zone and the water goes out in a weirdly far way, do not go out in the water. Do not go out there. Just get the hell, get the hell up. Because when these things happen, it's awful and there's nothing you can do. I mean, they're just so big. There's really nothing you can do. Yeah, so I think I showed this here. Like, this is what happens, right? Normally, it would be like that, and the water rushes back. And you're just so, it's only natural to be like, whoa, what's going on? And you walk out there. So don't do that. The other kind of boundaries you have are these divergent boundaries that can happen in between plates that are coming out, and they create these rift valleys. So there are these oceanic plates that are called mid-ocean ridges, for example, that create these rift valleys that are interesting geological places. A really cool place where there's a ridge where basically crust is coming apart and new land is coming up is Iceland. So Iceland is just an amazing place. It's called the land of fire and ice, right? It's far enough north that it's very cold, but it's also in a place where the land is constantly being recreated. So the crust in Iceland, so the land on Iceland is some of the youngest land in the world, okay? And it's just an amazing place because there's volcanoes going off. It really seems like the place is alive with young land if you go there. There's constantly eruptions. It's a very, very interesting place. And it's a place where you have this division. You have these two ridges that are coming apart, that are sort of breaking apart there. It's basically making the island of Iceland grow. So it's a very young place on Earth. Another way you can get islands in the middle of the ocean is a different way, okay? And Hawaii is a very different kind of island. Hawaii was created because there's a hot spot here out in the middle of the Pacific Ocean where basically it's prone to sort of a spot where lava is coming up. And the Pacific plate is basically moving over this hot spot. So there's basically a little crack up here where it's very prone to stuff coming out, and the Pacific plate has drug over it. So if you go to the Hawaiian Islands, okay, and if you go to the big island of Hawaii, the big island is the young island. Okay, this is the newest of the Hawaiian island chains, and in fact there's a brand new one that's being sort of created off the coast of the big island, where it's bubbling up and it's now beginning to grow under the water. But if you go down the chain, say to Kauai, Kauai is the oldest of the Hawaiian Islands, of the big Hawaiian Islands, and it's like about 4 to 5 million years old, where the big island of Hawaii is only about 700,000 years old. And I don't know whether or not this is true, but have people been to Kauai or the Big Island? Who's been to the Big Island? Who's been to Kauai? Who's been to Hawaii, period? Okay, yeah, so good fraction. You were not that far, so we're lucky we get to go there. Kauai seems to me like a more diverse place. Like it just seems like there's so many different plants, and just it's a very lush place. There's all these rivers and stuff. Where Hawaii just kind of seems more barren. It seems younger. It seemed, and I'm not a geologist, so I don't know if that's actually true. But it's sort of aesthetically, it could be just sort of psychologically, it seemed like a place that had more diversity than the Big Island. I don't know if that's true, but it's a very interesting place to be. You really get a sense of sort of this geology, this geologic history of the place being alive when you're there. You can see this too with island chains, okay? This is the direction with which this plate has been moving. All right, and you sort of see these kind of chains dragged across by these little hot spots that get built up on the Earth. So it's just cool, if you think about it in that perspective, it's really neat because you see the Earth as sort of this thing that's changing, that's constantly responding and sort of alive in that sort of qualitative sense, right? The surface of the Earth is constantly being turned over, and really it's places like Hawaii and Iceland where it's so viscerally true. So, big point here then is that the Earth is dynamic and evolving. The surface has been reshaped over and over again, and that's why the surface of the Earth is much, much younger than the Earth itself. The rocks have been cooled out over a period of time that's much, much younger than the age of the Earth. So most of the surface of the Earth is sort of tens to hundreds of millions of years old, which seems very old to us, but of course the Earth is billions of years old. So it's really relatively young in that sense. The big reason why the Earth is still active today is that the interior of the Earth is hot. If the interior of the Earth were not hot, all this convective kind of bubbling would stop and the Earth would become sort of a dead geologic planet. The tectonic activity may be an important point, may have played a very important role in the habitability of the Earth, by the way, and we'll return to that in subsequent lectures when we talk about the makeup of the atmosphere and something called the carbon dioxide cycle. The carbon cycle on Earth is, we think, intimately related with the fact that we live on an active planet. Okay, in the last few minutes we have left, I'm going to turn and talk about the Earth's atmosphere to give an introduction to the Earth's atmosphere. Here we're seeing the Earth's atmosphere viewed on edge, okay? So you see that's the land, and this is taken from, I think, the space station. So that's the sort of, you see the edge of the land there, and this bit right here, that's it. That's the atmosphere. So this thin, thin layer on the surface of the Earth is what kind of protects us from so many things. As we mentioned before, when we were talking about sort of the origins of chemistry and sort of proto-chemistry, the Earth's atmosphere is mostly nitrogen, okay? Molecular nitrogen and molecular oxygen. So it's about 21% oxygen, and we like that oxygen, we breathe that oxygen, so we're very happy about that. The other stuff that makes up the atmosphere is water vapor. So we have a fair amount of water vapor in the atmosphere. There's some argon floating around, and there's a teeny tiny amount of carbon dioxide. It's only 0.038% of the atmosphere of the Earth is carbon dioxide. But it turns out that this carbon dioxide, as we'll find out a little bit later, is a really important gas because it's responsible in good measure for something called the greenhouse effect that exists on Earth and keeps the Earth much warmer than it would be otherwise. It's the water vapor and carbon dioxide that are the most important greenhouse gases on Earth, and they give us a boost of about 30 degrees above what the temperature of the Earth would be otherwise. So if you took away the greenhouse effect on the Earth, we would basically have a frozen planet. There'd be very, very little liquid water on the Earth if you removed these gases. It's a testament to how effective a greenhouse gas, carbon dioxide, is when you see just how small a percentage of the atmosphere that it makes up, but how important its effect is for the greenhouse effect. There's also a bit of methane in the atmosphere and a bunch of other gases that are inert. That means they don't really bind with anything or easily create other chemicals. And then also there's other particulates up there in the air, like silicate dust and sea salt and sulfates, so dust gets kicked up into the atmosphere as well, so all this stuff is kind of mixed up there. Now, as we look at the atmosphere, it goes through, you can sort of take a broad brush and ask, what happens when you move up into the atmosphere? Now, a very important thing that we'll return to later is the atmosphere creates a pressure, okay? Even though air seems to be extremely light, there's basically a lot of it piled on top of our heads, and that creates something called atmospheric pressure, okay? So at sea level, okay, there's a pressure from the atmosphere that amounts to something like 1 kilogram per centimeter squared, or 14 pounds pushing down on us for every square inch. So we don't feel it because we've basically grown up with this pressure, okay? But there is a strong pressure, there's basically weight down on us because of this. It's in direct analogy to, if you felt a related pressure if you've ever gone deep diving, okay? If you go to the bottom of a swimming pool a deep enough swimming pool, you'll feel it in your ears, right? Does anybody scuba dive? Nobody scuba dives, really? Does anyone scuba dive? Never? You guys, oh, there we go. Good. So what do you do when you get down deep? When you start going deep, what do you have to do? You don't know? Okay, so so when you get down deep, right, you start feeling pressure in your ears. It starts hurting your ears. And if you go scuba diving, you have to clear your ears out. You have to blow. You have to do this trick where you close your nose and you blow really hard and you blow your ears back out. And then you can go dive deeper and deeper. Otherwise, it'll crush your eardrums because the pressure is so strong underneath the water. Okay? You guys are such academics. You just study all the time and you don't do these kinds of things, which I'm fully behind that. Just keep studying. It's great. But every now and then you should go do stuff like scuba dive and go see the aurora borealis and stuff like that too. Yeah, so you feel these deep pressure underneath the water, okay? And the same thing is happening when we're on land. We're basically underneath all this stuff, but we don't feel it because we're used to that. We're used to that atmospheric pressure. Now, if you go up higher in the atmosphere, okay, let's say you go up to a height of about 5 kilometers, okay? So a very tall mountain. There's a lot less atmospheric pressure. That's why your ears pop when you go up into the mountains, right? Your ears will pop. As you go up to 11 kilometers, there's only 25% of the atmosphere. Okay, so the point is, if you go up just 5.6 kilometers high, up on top of a mountain, okay, you've already traversed half of the atmosphere in terms of mass. Half of it's above you and half of it's below you. If you went up to the peak of Mount Everest, okay, which is about 8,800 meters, the pressure is only a third of sea level up there. The atmospheric pressure is only a third of sea level, which means 2/3 of the atmosphere is beneath you when you're up there. Okay? So not only is there less oxygen, there's a lot less air pressure. And that changes things. Like, for example, when you boil water, right, it doesn't boil at the same temperature it does at pressure at sea level. You got to cook your food for longer and stuff like that. So if those of you who've hiked up in the mountains, you may know heard something about that. Right. Once you go up to 56 kilometers, it's only 0.1% of the atmosphere is above you by mass. Okay. Okay. So one of the interesting things then is if you look at the atmosphere, people who study the atmosphere break it up into 5 different layers, 5 different what are called thermal layers in the atmosphere. And I'm not going to test you over these layers, but I just want to give you a sense of what's going on. As you go up, so this bottom layer here is called the troposphere. And 75% of the atmosphere is in the troposphere. And the troposphere basically is as high as the tallest mountains. Okay. And as you go up to higher and higher elevation, the air gets colder. And that's something we're naturally familiar with, I think, right? You go up high, it's much colder up on top of mountains than it is down below. The pressure's going down, the temperature's going down as you go up. The next layer, though, there's a next layer that's very interesting. It's called the stratosphere. We've probably heard the word stratosphere before. This is where airplanes fly, up in the stratosphere. The reason why airplanes fly up high in the stratosphere, commercial airplanes, is because there's not much turbulence up there. There's not much convection. Okay? Remember, convection is this thing where it's hot on the bottom and cooler on the top, and you tend to get this sort of cycling of air, and that creates turbulence. But once you get up in the stratosphere, it turns out the temperature profile stabilizes, and things are pretty constant temperature with height. That's because the ozone layer is somewhere in the stratosphere. And right around here, the ozone layer is basically absorbing heat from the sun, interacting with UV light from the sun, and heating up. So it's not only blocking that UV light, but it's also heating up. And there's sort of an additional heat source right here. So whereas naturally you would cool down going up, there's an additional heat source right here, and that stabilizes the temperature. That keeps that band of air very stable. So it all has about the same temperature. That stabilizes the turbulence. And that's basically why airplanes fly there, because it's a very stable place to fly. That's why you tend to get more turbulence as you're landing or taking off than you do when you get to a height. You know, when you're at 30,000 feet, it's usually, not always, but it's usually pretty smooth there. That's why commercial airlines do that. Okay? They have to pressurize the cabins, because as you go up this high, the atmospheric pressure drops. And so that's why you have to pressurize the cabins of these kind of aircraft so that you can fly up there where it's smooth. Okay? Biplanes, right, where you don't have a pressurized cabin, they fly down here, but they also get a lot more turbulence. Okay. Questions about that? Okay. And then there's other temperature profiles. I'm not gonna test you over this stuff, but you know, the layers of the atmosphere are very interesting, and they have this sort of complex temperature structure. But while effectively the atmosphere goes really, you know, is really, really deep, most of it by mass is down here. Okay, so it's very dense down at the bottom, and it gets lighter and lighter as you go up to the top. Okay, this is just another. I just put it here. I'm going to put this online, and you can look at it if you want to look at this. There's more of this here. Okay. So about 50% of the atmosphere is below 5.6 kilometers. About 90% of the atmosphere is below 16 kilometers. That's extremely thin. So if you think about, you know, what all the atmosphere does for us, okay, all this air we breathe and this protected layer, it's only 16 kilometers of this vast, vast Earth that we live on, right? So it's a very thin layer, but it does so many important things for us. It's very important. Okay. So next time, I'm going to move on and talk a bit more about the Earth's atmosphere. I'm going to talk about the greenhouse effect, and I'm going to talk about why we don't have so much hydrogen and helium in our atmosphere and why that's important. Okay, see you then.